Welcome to our buffers notes video. So this is back in your printout that you created a few weeks ago now, I think. This is all going to be about buffers. So the common ion effect is used to create buffered solutions. So think back to our acid-base notebook. We had some common ion situations where you mix together let's say like you mix together ammonia, which we know reacts with water to form NH4 plus and hydroxide. And then you could also mix that with like NaOH, it's strong, so I use the one-way arrow, and you'd end up with sodium and hydroxide. And so if you'll notice, we have hydroxides in common. This is called the common ion effect. And so we use the common ion effect to create solutions that are buffered. So buffers, what they are things that allow you to resist changes in pH. They will keep the pH from changing. And typically a buffer is made up of a weak acid and its salt, or it could be made up of a weak base and its salt. So an example of that, I think we're actually going to have some examples soon, so I'll leave it alone. When small quantities of strong acids or strong bases are added to a buffered solution, the changes in pH are small. So if you have some sort of system where you know you always want the pH to stay somewhere close to 9, then you can create a buffer that forces it to stay close to 9 no matter what you add to it. That's the advantage there. Okay, so here's an example, making a buffer with a weak acid and its salt. So here we have CH3COOH. What's the name of that? It is acetic acid, which is weak, so that's why we have a two-way arrow here. And we know it reacts to form hydrogen and acetate. And we're assuming that we have added a lot of acetic acid. We know in this situation equilibrium will lie very far to the left because weak acids don't really ionize very much. They're not going to release very many hydrogens or acetate ions. Salts, however, completely dissociate. There's a typo here. Go ahead and add Na to this. So this is NaH3COO. So this would be considered the salt that belongs to acetic acid, because we know acetic acid creates acetate ions, and so does this salt. It also creates acetate ions. And the nice thing about salts is that they completely dissociate, so you use a one-way arrow. And since they completely dissociate, you are able to create lots and lots of that ion that go with the original acid. So this system, when you mix acetic acid with its salt, so it would be sodium acetate, it will have a whole lot of the acetic acid because it's weak, and it's going to have a whole lot of its conjugate base, acetate, which is going to come from the salt. So you'll have a whole lot of everything on both sides, and that will be a buffer. So buffering capacity. Buffering capacity is the ability of a buffered solution to accept protons or hydroxide ions without a significant change in pH. In other words, you can add a whole bunch of acid or add a whole bunch of base and the pH won't change. The higher the concentration of the weak acid or base and its salt, the greater the buffering capacity. In other words, the more that you have of everything on either side of that arrow, the better the buffer works. So the best buffers, most buffers, are made with fairly equal concentrations of your weak substance and its salt. So you'd have like, what was our previous example? We'd have fairly equal amounts of acetic acid and fairly equal amounts of that with its salt, which would provide acetate. So we'd have a whole lot of acetic acid and a whole lot of acetate in a good buffer. All right, so here we have a new equation. It's called the Henderson-Hasselbalch. I think that's how you'd pronounce it, equation. It's probably wrong. Oh well. And this is your equation. So the pH is equal to the pKa. So what does that mean? What's P stand for here? Negative log. So we've got the negative log of the Ka equal to the negative log of the hydrogen concentration. Okay, so the negative log of the concentration of your hydrogen ions is equal to the negative log of the Ka plus the log of, I'm just going to go ahead and rewrite the whole thing, the log of your concentration of the ion over the concentration of the weak acid. You could also think of it as the log of the conjugate base over the acid. This also works in the other direction. The pOH is equal to the pKb plus the log of the concentration of the weak base and its salt. So here's our weak base, and here is what the salt provides. When the weak substance and its salt are equal in concentration, then you end up with a pH that's equal to the pKa. And this makes sense if you want to try plugging it in your calculator. Try taking the log of 1 over 1. You have an equal concentration of the substance and its salt. So 1 over 1. 1 is equal to 1. If you take the log of 1 over 1, you end up with 0. If you take the log of 5 over 5, still 0. So when the concentrations are equal, this log over on the side goes away, and you end up with pH is equal to pKa, or pOH is equal to pKb. So this is something that could speed up your problems when you're working. You also want to know how to analyze the inequalities here. So when the pH is less than your pKa, then that means we have more weak acid than the base from the salt. So in other words, we'd have, if I were to like draw this visually, more of the acid. So this, HA would be more, and we would have less, so less of our A minus. I'll make it smaller. That is an H, not a weird W. Now, if your pH is greater than your pKb, then that means that the base from the salt is higher in concentration than the acid. So if you were going to draw this visually, you'd have way more of this. It's the conjugate base that came from the salt, and less of your HA. Sorry if you can hear that. Somebody outside has decided to rev their engine all day. Oh well. All right, so here's a little problem. A buffered solution was created by mixing solutions of acetic acid and sodium acetate at 25 degrees Celsius. The final pH was measured to be, I'm going to write this out, so pH is equal to 2.89, and the Ka is 1.8 times 10 to the negative 4. And we want to know, what do we have more of? Which species has the highest concentration? Do we have more of our initial acid, or do we have more of the base that comes from the salt? We know in order to do this, we want to compare pH to pKa. We want to know the comparison. So in order to do that, I need the pKa. So what's the pKa equal to? What's the equation? Negative log of the Ka. So you'd have negative log of 1.8 times 10 to the negative 4, and you should end up with 3.74. So I have 2.89 as my pH, is less than 3.74, which is my pKa. So if my pH is less than my pKa, that means that my weak acid is higher in concentration than the salt's base. In other words, my concentration of acetic acid is greater in concentration than its base, which comes from the salt and partially from itself. So weak acid, salts, base. Okay, cool. Let's go on. So what we're going to do now is we're going to practice creating net ionic equations, which I know have been problems for people in the past, so let's try that. Hydrobromic acid, HBr, is added to a buffered solution containing acetic acid and its salt. So acetic acid would be CH3COOH, and its salt, it could be anything that replaces that H, so something that's positive. How about sodium? Oops. CH3COO. So there's the salt. Determine the net ionic equation. Okay, so what I'm going to do first is I'm going to list out all of my net ionic equations for each of these individually. So I know I have, this won't be the net ionic. I'll just write out what this becomes. So it's a strong acid, and it's going to become H plus Br minus. I know that my acetic acid is not strong, so what kind of arrow would I use? Double-sided, and that's going to be important later. This is reversible. This releases that hydrogen off of the end. It sets it free, and we end up with that. And then the salt. So we know that salts completely dissociate in water. This is all aqueous, assume that. So we'll end up with Na plus CH3COO minus. Okay, so here let's think about this. We have hydrobromic acid, that's an acid. And acetic acid, oh, that's another acid. So that's not what we want. We don't want to be showing hydrobromic acid being added to another acid. We want to show it reacting with a base. And I know that acetic acid creates a conjugate base. So what I'm going to do is completely flip this reaction around, and I'm flipping this one because it's the only one that's reversible. So I'm just going to go, whoop, that goes away, and I'm rewriting it now in the other direction. I want to show that hydrobromic acid is interacting with a base. So I'm reversing the only reversible reaction to provide that for it. Okay, so now if I was to write this all out, cram all the reactions together, I'll have HBr plus NaCH3COO. Now I'm writing this all out step by step, and that does not mean that when you do this on tests and such that you have to. You can probably skip a bunch of steps. Oops, oh no, out of space. Okay, so now I want to figure out what this looks like with its ions. So HBr, well, I know that strong acids completely dissociate, so in the ionic equation I need to separate them. I know that salts also completely dissociate, so I'll separate that one as well. I've already got this one separated. That doesn't separate further. And then I've got my hydrogen. Reacts to form. Okay, I'll have to write this underneath. So I've got my, actually that kind of works out fine. H plus Br minus. This is from my reactant side. Over here, I'll circle it. Right now I'm drawing this one. I just ran out of space, so I'm writing it underneath. Plus CH3COO minus. Now I'm not going to break apart this acetic acid because it is weak, so it does not get broken into its ions. Alright, so take your other color. We're going to cancel out everything that we can. Hydrogens go. Bromide, sodium, acetate. Oh, that acetate stays, this hydrogen stays, that acetic acid stays. You end up with a net ionic that is going to make you angry because it's, Basically exactly what we had before. Wonderful. Well, we know that this is reversible, so we can go ahead and do that because we have a weak substance over here and its conjugates. Okay, well that's that one. Let's try another. Sodium hydroxide. So this one's on the second half of your page. I just split mine onto different slides. Sodium hydroxide is added to a buffered solution. So sodium hydroxide. I'll just go. Oops. Oh, why isn't that working? Oh dear. Here, let's just do this. Here's a new layer. I think I should be able to write on that. Yep. So you can just read on your slide then what I'm doing. It says sodium hydroxide is added, so NaOH, is added to a buffered solution containing hydrofluoric acid. Is hydrofluoric acid strong or weak? The masses say weak. And it's salt. So again, it's anything that replaces the hydrogen in that HF, so I'll just use NaF. You could have done any other positive ion there. So NaF, and I know that salts completely dissociate, so NaF minus. Okay. Now, let's see, we have NaOH, and I want it to react with an acid. NaOH is a base. I want it to react with an acid. Is this written so that it will react with an acid? Yes, it is. So I don't have to flip anything. So I'll write this all out, all crammed together now. NaOH plus HF plus NaF is going to react to form Na plus OH minus plus H plus F minus plus Na plus F minus. Phew. Okay, now I'm going to split things into their ions. I know that NaOH becomes Na plus OH minus because it is a strong substance. I know that hydrofluoric acid is weak, so I cannot split it. And I know that NaF is a salt, and so those will also dissociate. Then I have what I originally had over here, this giant mess. Okay, so now I'm going to cancel out what shows up on both sides. I have a sodium on both sides, hydroxide on both sides, another sodium, another fluoride there. Okay, so your answer for this would be just your initial weak acid dissociating as usual. All that work. All right, well, there's your buffer video. Titrations are next.